Hello guys, this is Camille Gamarcha, the in charge of discussion in this group.
Hello guys, I am Janelle Rosette G. Pineda, the in charge of the procedure in this group.
Hello guys, this is James Kurt Ayun, in charge of the table on this video.
I'm Will Rose Castellano, in charge for the analysis of this group.
I am Dr. Paul Mayari, the in charge of the conclusion in our group.
Hi, I am Justin J. Peron and I'm in charge of the editing of this group.
In our laboratory experiment 5, we are to verify the principles that govern the resistances which are connected in series, and the material that we are going to use is the FET simulator, the circuit construction kit DC. We first made a circuit including a battery, 2 wires, 2 resistors, 3 ammeters, and a switch, and arranged it in a series connection. We then set the resistors to our desired values, and we input it in R1, R2, and RT. After setting the values to the resistors, we then attached the voltmeter to the two resistor 1 and 2 and connected the ammeters to get the values of V1 and V2. For the total voltage, we placed the voltmeter across the circuit. To get the values of I1, I2, and IT, we just simply looked in our ammeter. We did the same process in all 3 trials.
In the series, the ampere are a fixed value and applied to the same rule on each trial. For the first trial in resistance, the total resistance is the addition of the first and the second resistance, which are the 30 ohms and 40 ohms, is equal to the total of 70 ohms. In voltage, we added the first and the second volts, which are the 10.29 volts and 13.71 volts, results to the total of 24 volts. For the second trial, in resistance, we added the 50 and 60 ohms to get the total of 110 ohms. In voltage, the addition of 10.91 volts and 13.09 volts are equal to the total of 24 volts. And for the third trial, in resistance, the addition of 70 and 80 ohms are equal to the total of 150 ohms. In the voltage, the addition of 11.20 volts and 12.80 volts are equal to the total of 24 volts.
Resistances are said to be connected in series when they are joined such that the current passing through any one of them is the same current passing through the other resistances in the combination. If there is no accumulation of charges at any section of the combination, the current passing through the resistance is the same current I, which is also the current through the group. Ohm's law may be applied to the whole group and also to each resistance in the group. The total voltage across the group Vt is equal to the sum of the separate voltages across the resistances in the group. The equivalent resistance of the combination is equal to the sum of the separate resistances. It is clear from the arrangement that appliances in series cannot be controlled separately. When one is disconnected, the rest will also be disconnected. This is the principal disadvantage of a series combination. Where do we often use series connections? In the case of streetlights, lamps are sometimes connected in series for uniform brightness. If they were connected in parallel, the lamp farthest from the source of power will be too dim unless the voltage was stepped up. For safety reasons, series connection is also advantageous for Christmas lamps. The tail of a car is connected in series with a pilot lamp on the panel board, so the driver can tell right off if his tail is working or not without having to look at it. This is the table for our data. For trial number 1, resistance 1 is equal to 30 ohms, resistance 2 is equal to 40 ohms, and the total resistance is 70 ohms. For current 1, we have 0.34 amperes is equal to current 2, 0.34 amperes, and equal to the total current 0.34 amperes. For voltage 1, we have 10.29 volts. For voltage 2, 13.71 volts. And for the total voltage, 24.00 volts. For trial number 2, we have resistance 1, 50 ohms, resistance 2, 60 ohms, and the total resistance, which is 110 ohms. For current 1, 0.22 amperes, equal to current 2, which is 0.22 amperes, and also equal to the total current, 0.22 amperes. For voltage 1, 10.91 volts, voltage 2, 13.09 volts, and the total voltage rather is 24.00 volts. For trial number 3, resistance 1 is equal to 70 ohms, resistance 2, 80 ohms, and the total resistance is equal to 150 ohms. For current 1, 0.16 ampere, for current 2, 0.16 ampere, and for the total current, 0.16 amperes. For the voltage 1, we have 11.20 volts, voltage 2, 12.80 volts, and the total voltage, 24.00 volts.
For our analysis, we are given 3 sets of data with 3 trials. The given data are divided into resistance, current, and voltage. As you can see on the table, the total resistance increases while the total current decreases, thus making it inversely proportional, while the total voltage remains constant. As Ohm's law states that the electrical current flowing in a circuit is proportional to the voltage and inversely proportional to the resistance. Therefore, if the voltage is increased, the current will increase provided that the resistance of the circuit does not change.
Therefore, we conclude that if the voltage is increased, the current will increase provided that the resistance of the circuit does not change. To put it another way, if we raise the resistance, the current is directly proportional to the resistance, while the overall voltage remains constant.